So the representation of the fractional numbers with floating point demonstration actually creates some errors. That's why we have round of error, um, because we have a final number of significant figures and round of error occurs. And let's show how it works. This is the example of the previous slide. Actually, we have the 7-bit word with maximum is 7. You can see here. And we will define our errors based on this example. And I just want to write some numbers here. For example, we calculated 6, 5, and 4. Then here, actually, there are some numbers. And we have the interval of 1 here, you can see. And the rest, the small, if you remember, it was getting smaller in these locations as well. So we have a difference between two x's. These are x values as delta x. And we will have some errors. First of all, let's start with this one, overflow error. Overflow error means that after some point we are not able to show any values. So for the 7-bit example, for instance, the maximum number we can show is 7, and if we try to show a number larger than 7, it becomes an overflow error. Second, underflow. Underflow is that we cannot show some numbers smaller than the mantissa value, which is, for example, we said that mantissa is smaller than 1 divided by b, divided by 1. So if we try to show smaller numbers than this, then it becomes underflow. So very small numbers cannot be represented. And we showed this in the previous example already, that we cannot show some numbers smaller than 100. So other errors, especially the round-off errors, is chopping, due to chopping and rounding. So chopping means we actually cut a number, but we don't change the last number based on the next number. What I mean is that, for example, let's think about pi value. So pi, you know that it is an infinite fractional value with 3, 14, 15, 92, 6, 5, 3, 5, 8. So it goes like this. So let's say we want to chop this off after 2, after here. So chopping means we can just write p as chopping 3.14, 15, 92, and we don't change this 2 based on this value. So because it's 6, actually we need to increase this, but we don't do that. We just write whatever we see here, 2. And in this scenario, the error between true value, which is the top one, between this and this is 65 times 10 to the power minus 8. So it's still very small, but there is a round of, this is round of error. Round of error due to chopping. But what we do normally in engineering, if you know, as you know, let's say, we see a number greater than 5 here, we increase this to the next value. So that means for this example, pi for rounding should be 3.14, 15, 93. So this should be 3. And if we have the 3 number here, then we will have a true error, rounding error of 35 to the power 8. You can see the true error reduced actually. This is the, let's say first, error, round of error for rounding. And you can see that when we did rounding, we actually reduced the error. So this is advantageous for us. But because the error is very small to the power minus 8, it's very, very small, we can ignore rounding process, because this procedure will check the next number, and if it is greater than 5, it will increase this number by to the next one. This will require an additional computation in the computer, so it will create a computational cost and it will take time. Actually, today the computers are very fast and you don't even feel that rounding process. It rounds, but you don't feel the time lapse, but still it is an additional time, so it actually spends some resources, let's say. That's why some computers or some coding programs do not round unless you specify it. It just chops because the errors are small and reduced computation time. It just do the chopping, and if you say, okay, do the rounding please, then it will do the rounding. So that's why we can represent this in two separate errors. And as we said, it requires additional computational cost, the rounding. And it is the same for any other numbers as well. This was just an example, but these are valid for other numbers too. So finally, we have number 5, the interval between the numbers, that means delta x. This delta x actually increases as the numbers grow in magnitude. So we mentioned this already. Here the increase in numbers was smaller, then here it is larger, then it is further larger, then here it is the largest, for instance, with 1. So they grow in magnitude. And if we normalize for normalized floating numbers, chopping and rounding have different increase of these growing. So for chopping, delta x divided by x should be smaller than a threshold, and for the rounding, delta x divided by x should be smaller than a threshold divided by 2. And this threshold is defined as machine epsilon, and it is given by the base system value to the power 1 minus t, and t is the represented digits. So we will use this formulation especially to have a threshold for chopping and rounding errors like this. So we will have an example in the following slide for this purpose. Let's use the same example as you can see on the right hand side for 7 digits for determining the round of errors using the machine epsilon criteria as well. We want to determine machine epsilon and also verify its effectiveness in characterizing the errors. And we will assume the chopping is used. So let's first define the machine epsilon. And if you remember the formulation, the machine epsilon was b to the power 1 minus t, and t was the digits. And for the digits, we will use the digits of the mantissa. So the mantissa digits is actually t is 3 for this case. That's why this is 3, and b is 2 because it is in base 2. This is base 2. That's why the result is 2, 1 minus 3 is equivalent to 0.25, which means that the relative error should be bounded by 0.25 for chopping. If you remember, for chopping, it was just this value was the bound. And if we remember the values from example 3.5, example 3.5, if we draw them here, it was like this, and in the beginning regions 0.0625, 0.07, 815, 0.09375, and 0.109375. And finally here 0.125. So at this area the increase was the same and only 0.015625 difference. And after this the difference was different. Now let me write them down to 0.125 we said, and let's increase the difference 0.15625. These are the values that we determined in example 3.5. So you can go back there to remember these. 0.1875 and 0.21875, and it goes like this. After this it will increase again, but up to here the difference is 0.03125. So at this region, I mean, once the difference started to change here, especially, this is the upper bound of first interval. First, let's write first as well. Then, you know, the second one finishes. This is the upper bound of the second interval, for example, etc. It goes this way. So what we need to do is we will have an example. Let's say we use this 125 and 15625. Let's use these. If you remember, for 0.125, the 7-digit demonstration was, first of all, it is positive 0, and the exponent is negative, and the exponent 10 is 10, and for 125 it is 100. So it was one. You can calculate it to see if this is really correct. And the next one, this one and this one, we want to check the next one. It is 0 again, 1, 1, 0, and the next one was 101, and this gives 0.1. This one is equivalent to 0.15625 in 10 system. This is also base 10. And the difference between these is, as we said earlier, ET 0.03125. The difference between these two. So the difference, actually this is delta x, and we will have x is 0.25, for example, and if we want to have the relative error epsilon t, that is delta x over x, as we mentioned in the previous slides for the machine epsilon. This will give the machine epsilon value, and it has to be smaller than that when we have the rounding. If we divide by 125, for example, for this one, the result is 0.25, and this is same as machine epsilon, and machine epsilon is, for this problem, 0.25 anyway. So for example, if we have let me show that with maybe black color. If we have this value and want to have a cutting after some digits, let's say from here, we will have a value 1562, which is smaller than this, so somewhere here, and the error of this should be, round of error of this should be smaller than the difference, which is 0.03125. It will be smaller than this when compared to this one, and the relative error then will be smaller than this machine epsilon. So basically this has to be smaller than 0.25 when we have a rounding, for example, like here. Sorry, not this one, but the bottom part. So what we say is that the maximum error can be 0.25, and the actual largest is very close to here, so we can say a close value here has the largest relative error, and the largest value should be smaller than 0.25 for this problem. So this is how we use the machine epsilon as a limiting bound for the round of error.